Good evening. Tom Cherry Holmes with another video in the Retro Computing Archaeology, a series of videos intended to demonstrate a wide variety of retro computing subjects. With this video, we will actually show some of Atari's coin-op game development tools, namely the Mac65 macro assembler and linker that at coin-op to develop a variety of coin-operated games, such as Centipede. To do this, I have over here on this screen a little bit of some show notes on the left-hand side, and the right-hand side is going to be filled with either a terminal display or a web browser display showing off things that we will actually be demonstrating in context. In this case, we will actually be showing off here and developing changes for Centipede, game that was developed at Atari during 1980 and released in early 1980, and went through actually 4 different revisions throughout its production lifetime. In this case, we'll actually be dealing with revision 2, which was released on May 28th of 1980. Centipede itself is a custom. It's a custom computer designed specifically to play Centipede. It has connections for power, has connections to go to the monitor in the arcade cabinet, to the joysticks and various controls and buttons, and it also has everything that you would expect from a microprocessor-based machine, including a microprocessor, programmable interface adapter for input and output, and a number of ROMs you can see both here in the middle of the board and on the edge of the board to contain not only the program code, but also the picture data as well. We will be modifying some of the code in the code ROM. So, like I said, the goal here that we are intending to do is to demonstrate these particular development in context. To give a quick overview of the development system that's being used, then we'll use that development system to modify the source code, assemble the source code, link it, and then cut the resulting binary up into ROMs. Finally, we'll take and run the new ROMs on MAME with an integrated debugger used as an ersatz black box source. A little bit about the development system. You'll notice that this Centipede board right here doesn't have a keyboard, nor does it have data storage such as disk drives, cassettes, paper tape used to store code. So how do you do the development? You need some sort of larger machine to do the development on. And for coin-op, this was done on a 11. Something like this. We have right here a PDP 1123. This particular unit is from 1979, and the particular unit that I will be simulating is outfitted with 64 kilowords of 16-bit wide memory. We will also have a number of storage devices. You'll see that in this particular cabinet, we have the main computer unit right here in the middle, but we also have a variety of storage devices that are attached as peripherals to this central processing unit, namely a pair of floppy drives here, RXO2 in this case, and a pair of RLO2s for hard drive storage using hard drive platters cartridges. But in our case, what we'll actually be using, we'll have 3 RK05 cartridge drives here. Each of these drives can hold a particular platter that has 2.5 megabytes of storage, and we'll have 3 of them. So 7.5 megabytes of total storage that's available to this particular. We'll also have an RX01 floppy drive here that can be used for backing up the particular code onto 8-inch floppy drives. Each of the floppy drives is a standard IBM 3740 format floppy holding approximately 250. To get the code out, we need a way to get the code out. And in our case, we're actually going to be using paper tape punch. Yeah, funny, isn't it? So what you literally have here is a roll of paper tape. In this case, it's fan folded. And on this paper tape, you've got holes in it. Holes for each binary bit of a particular binary byte, all columned up and down the tape here. The middle part of this device is the paper tape reader. You take and feed it in here to feed in a paper tape into the computer. But you'll also notice over here on the right-hand side, this area right here is actually a paper tape punch, which we use to make new paper tape. Take it final testing system. Well, the roll for the paper tape for this guy is actually in a bin at the back of it. Finally, we need some sort of development console. You'll notice that 1123 that's right here didn't really have any sort of console. We have to actually take and provide one. We have to provide some way to input code into the system and to see what we're doing. So we're going to be using a very standard digital VT100 data terminal to the. Finally, the operating system that we'll be running is a copy of RT11 version 3, about 1977. It is a single tasking operating system, meaning it can only run one program at a time. Used for small teams of people for doing things like real-time data acquisition and development shops. It's just very small, very simple, very fast. Doesn't get in the way. Finally, a little overview of the black box itself. We need something to actually take and emulate the Centipede. We need something that can take the paper tape input in and take and use that to create EPROMs. And for that, we're actually going to be using MAME as our testing system, as well as for our debugger, which would normally be used and connected up to something like an HP, a logic analyzer. Did have a parenthetical here, and I will read it to bring the point across. Using paper tape as an example of the improvisation needed by old school developers to get artifacts to their destination. It is not indicative of the process. Got that out of the way? We can actually start the process of doing some code editing here. Okay, great. That we will take and bring the browser right here, open up our little code editing window here. For those that are following along in the description, there's a number of links. There's also a repository called the atari-coin-op-assembler. And this has a whole bunch of things, including a complete emulation environment that can be run inside this emulator. You can follow along too if you wish. We're going to be running PDP-11 from the SimH package with coin-op.ini. That's in this folder right here. This will do the job of setting up all of the different disks, as we can see right here. We have a system disk, which contains all our operating system and tools. We have a disk to contain our source code and our intermediate object code. And we'll see that there's another disk that's going to store our binary. And when we boot here, one of the things that you do not see that I do feel compelled to mention here is that SimH actually skips over the process of using ODT and the front panel to actually take and bootstrap the operating system into the computer. This is actually skipped over. So we're skipping over that step, and we've gone directly into RT11 here, and we're sitting at the dot prompt. At this point, it is waiting for a command for us to do the right thing. The first thing that we actually need to do is we need to take and do an edit. And for that, we need to use an editor. In this case, we'll use KED, the keypad editor. It's a full screen editor and was just introduced with this version of RT11. Really cool. So we will use the edit command, and we'll say we want the ed editor here. And we want to go ahead and use file on DK1 here, and we modify. Actually, let's do this a little bit. I'm going to go ahead and assign DK. And one thing you'll notice here, because RT11 was actually designed to be used by teleprinters such as the DeckWriter 2, when you hit a backspace, it actually prints the character that it gets rubbed out, along with a backspace to indicate that the backspace key was pressed at this point. You can see what you've actually taken and rubbed out. So now we're sitting just past the D key. I want to take and assign RK1, okay. And at that point, we can see a directory of the source code files that we have here in the directory. So if I want to see what's actually sitting on my system drive, for example, the tools that I have available, I can use -sy here to show sitting on my system drive. We can actually see down here at the very bottom, we have the tools that I've added here. LinkM, which is our linker that we're going to use, Max68, which compiles 6800 code, and Max65, which compiles 6502. There actually is another compiler here called Max69, which can compile 1609 code. Going back, we have a handful of files that comprise the individual bits of Centipede. We've got global defines for constants and the like. We have Centipede's IRQ handler. We have Centipede's picture data right here. The main Centipede file here, which you could probably guess because it's 105 blocks long, and Centipede's testing and diagnostic route, as well as the watchdog timer and a few are sitting here in Centia. We also have some reusable code right here, which is the coin accepting code called coin65 that Mike Albaugh wrote. And we've got a little bit of source code here, which is actually just raw prom data being read from a prom that creates the necessary sync prom that we. There's also, you'll see right here, a file called senti.com, and you might think, oh, that's an executable file. Well, actually, no. Com files are what RT11 called simple scripts. And if we actually take a look at it, we can see a preview of what we are going to do to actually take and build our file here. Namely, we're going to be running Max65 and passing these commands here to generate the object files, then running linkm to take and pull those object files into binary files. And then they have a file here called image file, which basically takes and splits this up into the individual proms that go into the board itself. We don't have that tool, so we actually have to take and we'll do that when we're not going to be using this because we're actually going to be doing these steps individually. Contact. But it's here nonetheless, so you can see it. The first thing that we need to do is we need to actually take and edit the code. And to do that, we are going to take and edit, we're just going to take and edit some of the text strings here that are actually present in the IRQ handler of all places, which is where they've stuck the text strings. We're going to use the edit command here, and we're going to use the KED editor, which is the keypad editor. It's a full screen editor. It's really great. It was just added for version 4 of RT11. Oop, looks like I accidentally dropped here. Oop, more time. So now we're sitting and looking at the first page of SimIR2. And on my VT100 terminal, I can use the arrow keys to go up and down and look through the source code file, and we can see the messages and things. Now you can see this is the fully commented original source code that the programmer used to write the game in the first place. The program, in this case, Donna Bailey and Ed Log wrote this source code, popped it in here, wrote it in here, and you can see all the original comments, which are very amazing from archaeological. It's worth a pass to just go through this and look at all of this. If you're familiar with 6502 assembler code, you can see that everything pretty much looks like it should. It makes sense. In our case, we're going to do something that we can see very quickly, and we're going to modify one of the messages. We're actually going to take and modify the high score. We're going to take and delete. Modify our, do our little modification here. Type it in. There it is, ready to go. We replace the high scores here. This will show up during the attract mode. Know that for absolute. Now that we're done, we actually need to take and inform the editor that we want to exit saving our changes. To do that, we actually need to press the PF1 key. Now, there is no PF1 key on a modern PC keyboard. This is a VT100, and it's sitting here on to the right on the keypad. I have to simulate this by pressing its escape sequence by hand. Case, the escape sequence for PF1 is escape OP. Sure to type capital OP. You don't see anything happen, but something did, and the next sequence will actually put us into command mode. We need to also now press the 7 key, put us into command mode. Escape OW, and you'll see that now we have a command window up top. Now we just need to type exit, making sure to type it in caps, followed by escape OM to simulate the keypad enter. We've now saved the file back at the dot prompt, ready for the next. Next, we want to go ahead and start to assemble the code. Now, I've already done the assign command up top here. So the default drive, DK, is now mapped to RK1. So that makes the next set of commands here much easier to see and understand. Recall that Max65 is sitting over here on the system drive. It's a save file, and save files are the equivalent of executable files for RT11. And to run them, we actually need to use the run command, which is abbreviated as R. R Max65. Once that's done, the asterisk command indicates that we are now sitting inside of Max65, and Max65 is now waiting for what is called a CSI expression. This is basically a way of saying, okay, we need to specify the destination file name, source file name, what we are going to assemble. Well, we're going to create centi2.object from centi2.mac, and for that, all we have to do is say centi2 equals. Now I'm running this PDP-11 assembly here at full speed on my machine. This only took 1.5 seconds. On the real system, this takes a few minutes. Once it's done, we see that there are no errors detected, and we have 14,275 words of core memory, that is RAM, that's available afterwards. This allows us to keep track of how big the code is and literally how much core we're using up while we're doing it. We need to do the same for the other files as well. Actually, we need to do one more file. So we need to do a sync. We'll see that we have, as part of this, we also need to make a special file called a sync prom. And it makes those now. At this point, we can then take and hit Control C to exit the program to go back to the dot prompt. We do a directory at this point. We're still on VK on RK1, and we can now see that in addition to the Mac files that we had before, we have the backup, which contains the file before we made the changes, along with the new version that has our change. We also have object files. These are what are known as relocatable object files. And that means two things, really. Mostly it means that any absolute addresses inside the files are changed into relative addresses. They can be shoved anywhere in memory, and any symbols that didn't show up here, stubs are placed for them so that they can be resolved by the next program that we're going to use, linker, take and convert all those relative addresses, absolute addresses, and while also resolving the symbols that were not found during this part of the assembly. And that's important because we've split the assembly across several different files here. We have to bring it all together, put it all into memory in one contiguous chunk of memory. We're going to use the linker for that. For that, we're going to use another tool called LinkM. This is called LinkM because this is quite literally like the Mac 65 tool right there. Mac 65 was an adaptation of Macro 11. I didn't mention that before, but the engineers at Atari literally took Macro 11 and transmogrified it to take an output 6502 assembler code. Well, that whole process required a corresponding linker that also understood the output from Mac 65 to produce absolute binaries. And so they made what was called the linker for microprocessor. Here. Process to start it is just like with the macro assembler. And the prompt's the same too, ironic. And this time, the same process here is being used. We have a destination, and that destination contains the final binary plus the listing equaling, and the source is the three object files that we created for this particular to go into this file here, and the same for SimH. So we're going to wind up with three separate files built from three sets of objects. And we're going to get three listing files out with that too. See so far? Okay, great. So go ahead and just cut and paste it in. And there's no problem with the linker. The linker didn't find anything wrong, so it immediately came back to a prompt. Do the same thing again here with SimH. We not actually output a SimH file? Okay, no problem. We can go ahead and we can go back to that. Oh yeah, sorry. And that's a my bad here. I will take and fix that right now. Have our first major glitch of the show here. One reason why I like using org mode for application notes, modify them. Okay, I'm going to go ahead and hit Control C here. I'm going to go back into the Mac 65 real quick. That right there. That's all I needed to do. I needed to make sure that that object file was created. Now I can go back in. This. You'll notice that since there's no issues here, it didn't have any errors, so it created the files. We can then hit Control-C to exit. And if we do a directory on DK2, we can now see our save files along with the map files as well. And if we take a look at one of these map files, the one that's going to make the most sense is Centipede. We can see what the linker did here. The linker, Atari Link M version 4 or 6 here, this is the load map and where everything is going to be placed inside the image. The absolute file starts at 0. It's 3366 hexbytes long. And after this point here, these are the global variables right here and where they are placed relative to that starting point. 58268887. Notice that there's a couple of interesting things here. One, you'll see a global symbol for copyright, and you'll see symbols for things like checksum, for example. These are important because basically if you change certain parts of the code and do not alter the corresponding checksum here, the game will blow itself up and throw itself into the watchdog timer indefinitely. Crashes. That's it. Game over. So you get an idea now of how the file is linked and where the code is relative to the start of the absolute here. I won't go into it here, but if you actually look at the references for the documentation, you'll see references to the start of where things actually fit in memory and start, and you can reconcile these addresses where things actually fit inside the memory map of the system. One thing that Atari did very well in coin-op was they had documentation for, and it's really something. But we need to move. Go ahead and end here and go on to the next step. Now we need to take and send these files to our black box. That we're going to use the paper tape punch to get this file off of this machine into a form we can carry over to our development system. To do that, we need to basically save these 3 files, put them into paper tape form. And for each of those, we need to temporarily take and I'm going to stop the simulation just for a second because we actually need to load the paper tape punch. Once we've loaded the paper tape punch, we can continue as if nothing happened. And I can now take and, let's see, copy DK2. Recall that we have those save files sitting on DK2. We need to take and copy those to the punch. Now, in reality, this will take a few minutes. Since we're in emulation, it's pretty. But now we have this big fanfold of paper tape they can carry over to our development system for this file. We need to do it for the other 2 files as well. Same thing. Attach the paper tape punch, extend pick, continue, and the sync prom. Continue. There we go. Now we've basically created these 3 files. And at this point, we can shut the PDP-11 off. We're done. There's no shutdown procedure, so we simply go back to the front panel, and we halt the system. Done. Now at this point, we have 3 files that we've created. Take a look at them a bit closer. We'll see that the picture data is 4K in length. The main Centipede binary is 16K in length. EPROM is actually 1,000 bytes in length. Funky, but we can deal with that. So the next thing that we have to do at that point, now we need to take and cut up each of these files and put them in the right place on our development system. Why do we need to cut them up? Well, because it basically, when the linker took and linked everything together, it created large memory image files starting from 0, address 0, going all the way down to the end of the last byte of code. And that really made some things kind of interesting. For the picture prom here, what that ultimately wound up with, if we take a look at it, is we wind up with picture data, of course, raw binary picture data here going all the way down for all the various graphical assets inside the program in the right order. But we'll see something rather interesting with Centipede, because Centipede's code actually begins at hex 2000 or 8,192 bytes in. First 8,192 bytes are completely empty till we hit address 2000, which is 8192 decimal. Once we do that, we immediately see that jump instruction going to the reset vector here, right at the start of right here at the start, along with the copyright message, which you must not mess with. Mess with this, game blows. Okay. Look at the source code, you'll basically see where it checks some, how it makes the game blow up. Point is that we've got all the code and everything. It's contiguous after this point, so all we have to do is skip past those first 8192 bytes and then skip 2K bytes for each prom after that point to take and align it into the correct place for each successive prom. Because what we have to do is take this big file and split it up so that they can fit onto individual 2716 prom images, kilobytes of do that. We would normally use, and if you looked up here when we were first looking at that command file and all of that stuff here, probably saw that we had that command file, and we were referencing a particular utility called image file. Again, we don't have this tool, so we have to actually take and improvise on our own, and we're going to use ed inside of it to take its place. Easy enough. We got to do, we're going to take and split each file up and put it in its destination. If it will let me, if this will. Okay. There's the first one right there. Bam. It skips over the first 8192 bytes here to get rid of those zeros so we don't deal with them. It writes out 2K worth of data. We set this just to make the count nice and easy to deal with. And if we look at the documentation's in the reference here. These are the ROMs, and these are the ROMs that MAME expects. They want to use the serial number for the ROM and the location, the grid location on the board where that ROM is placed. So we're more than happy to do. We're going to take and split we have. This is all we have. Bam, bam. Because I have it here, cut and pasted, I'm making sure. Oop. Really? Oh yeah, that's right. This is the going, wait a minute. Trust my instincts. So we've now split up the ROM, skipped over the parts we didn't need until the next piece for the next ROM, and we got all the ROMs in place. Now we're done. All the ROMs taken and split up, they're burned, they're in the development system, ready to go. At that point, I can then go over to the development system and we can see right here that we started and we immediately wind up fun times with, we haven't started the system yet, just we can see where we are relative to the beam position, our processor status registers, everything ready to go. At this point, I should be able to hit run and see something substantial. There we go. There's our hello world up here at the top. Centipede is running here. We can see it skipping along and working through its IRQ stuff, and we stop it, step into the. So there we go. We've done it. We've taken original Centipede source code. We've made a modification to it. We've gone through the entire assembly and linking process, pulled it out into paper tape so we can pull it into our development system, taking it into our development system and shown. And if you want to, we have the references, which I will take and paste into the video description as well, so that you can follow along. The repo that you want, if you take and follow along with everything that we've done here, is the atari-coin-op-assembler repository. But this repository also pulled from these two particular repositories. Atari tools came here over at Bitsavers, and the HistoricalSource repo has tons of coin-op games here that can be built with macro assembler. I also want to thank Al Kossow for hosting Bitsavers, which is absolute treasure trove of archaeological data for retro computing. It is a wonderful service, and if you haven't, just take and thank him. If you see him at a VCF show, thank him, because he has provided a wonderful that is useful to all of us. Geist was also invaluable for helping debug the last bits of the toolchain, where we were tracking down what wound up being an obscure bug with LinkM. The version of LinkM that's built on disk F8 of the Atari toolset is different, is an older version, and outputs binary files with slight differences, enough to cause Centipede here, for example, run. Turns out that the good source code, the source code to LinkM, was actually available on the E2, E3, and 4 disks used to build LinkM, which I've already done for the disk images that are here in this repo. I also want to take and thank the people running the HistoricalSource repo on GitHub, because it is full of all sorts of amazing bits of code archaeology. If you want to understand how these games work, the best way is to read the source code and to look through it all, try and understand it. And if you don't understand it, go on to the VCF forums and start asking questions, because someone will. With that, we're going to go ahead and leave this video here. I hope you guys enjoyed this, and I hope it provided a usable bit of context into how these games were put together inside of Atari Coin-Op, using the how these actual tools work. Until next time, guys.